I would like to welcome everybody to this. I forgot how many talks we already had in this series, so it's a very successful series right now. This series is around artificial intelligence, natural language processing in education, and with particular focus on educational assessment. There's more coming in the waiting room. We are very popular. And we are very happy to have a speaker today, Xiaoming Zhai from Athens, Georgia. He is an expert in science education and AI. And I met him during a meeting at the National Academies of Education in Washington, D.C., and we started talking and have a lot of common interests. Before he was in Athens, which is really nice and warm right now, he was in Michigan, and before that he was in Beijing, the Beijing Normal University. I have very fond memories of the Beijing Normal University as well. I was there once with the group that is doing the national assessment of educational quality there. And then there was also a very nice psychometric society meeting at Beijing Normal University. So if you have a chance, visit that place. It's really worth it. So I don't want to talk a lot more. Again, I think I don't even have to introduce much. This is just really amazing work. I was very happy that I got to talk to you, Xiaoming, at this meeting and immediately invited for this talk here at our Brownback lunch meeting, because I think this is highly relevant to see what's going on in science education. So without further ado, please take it away, and we're very happy to have you today.
All right. Thank you, Matthias, and for your introduction. And it's really a great honor for me to be here to talk about my research, and I appreciate everybody's time and to join for this talk. So for today, I'm going to talk about artificial intelligence-based next generation science assessment based upon some work I'm doing currently at the University of Georgia. So in Georgia, we are starting to found a new center, AI for STEM Education Center. And in Georgia, we are currently have an AI cluster high. So we're going to bring more AI in education faculty member here, new faculty members to Georgia. So that's some new initiative across campus going on. So for today's talk, so I wanted to first introduce a little bit my background. So actually I was a high school physics teacher for 9 years before I pursued my PhD at the Beijing Normal University, and my research originally focusing on assessment and like a learning progression, scientific modeling. So I also use like a machine learning and artificial intelligence, mobile technology to advance assessment work. So right now, my project primarily focusing on using AI, machine learning, data science, and learning analytics to facilitate innovative assessment practice for science teaching and learning. My major work are focusing on classroom, but I started to do some large-scale assessment since, I guess, maybe 2 years ago. I worked with James Pellegrino, and I led the chapter large-scale assessment in science education for the handbook, the third version of the handbook in science education. So currently, my work focusing on science teaching and learning, we really are interested in some complex construct in science, like scientific modeling, argumentation, computational thinking, explanation, understanding of some cross-cutting concept like energy, and also some discipline quality like force and motion, or some like problem-solving skills or scientific consensus, or students' learning progression, things like that. I'm also interested in assess teacher, especially like a teacher's pedagogical content knowledge and a teacher's instructional decision making. So we are trying to use assessment to facilitate teachers and help teacher this instructional decision making. So my work using automatic scoring like natural language processing, computer vision, and we are trying to increase the scoring accuracy, and we are also examining scoring bias, and we also focus on develop some new algorithmic models. Like I'm going to briefly talk about that later. I also worked on using some learning analytics skills to analyze some log file data. We have some publications like focusing on the processing data from OECD's the large scale assessment. Currently, I'm also working on some project. We are focusing on examining using eye tracking data to examine the undergrad students' learning of chemistry concepts. And we also use cognitive diagnostic modeling to analyze some argumentation skills and some other work. Part of my work, from scoring and towards like how to support the teacher. So in order to support teacher, we also focusing on developing dashboard. So we use human-centered design approach to develop dashboard and we are piloting a platform with my collaborators from Michigan State University, West Ed, and University of Illinois, Chicago. And my work also covered a little bit about adaptive learning and the testing work. And also recently we are focusing on developing a new approach we call AI-based learning or AI-based scientific inquiry. So I'm working with my students and a school district near Georgia. We are trying to incorporate AI into scientific inquiry. And we also working on some robotics and the game-based project. Here's my part of my team. So and my partner and my collaborators. On the right side of my students, doctoral students who worked with me. In today's talk, I'm going to primarily focus on two aspects. The first, I'm going to briefly talk about why is AI for next generation science assessment. And the second part, I'm going to use, I guess, 3 individual study to answer present how I apply AI to assess and promote next generation science learning. I want to start this roadmap. Probably you're very familiar. We are always interested in understand how students know, right? That has been multiple decades from the book, like how people learn, know what students know, until maybe 10 years ago, right? In science education, we have a framework, new K-12 science education framework released, which introduced the 3-dimensional science learning, including the discipline core idea, cross-cutting concept, and science and engineering practices, and also introduced the learning progression, right? So the major 2 features from this framework, and the US further the following years developed the next generation science standards, which has been adopted by more than 20 states and adapted by, I think, 24 states, other states. And in 2014, the NIC released the assessment report, especially focusing on how to develop assessment to be aligned with the NGSS, the next generation science standards. And here we realized a lot of challenge, so which led to my current work, like apply AI to assessment work. So currently we are broadly focusing on AI for STEM education. So I'm going to unpack a little bit here. So the three-dimensional learning are presented as some performance expectations. So if we look at the next generation science standards or some state standards who kinds of different from NGS, but very similar if you do compare them. What we did, the standard did was like present some statement we call performance expectation for students from K to 12 levels. So each grade levels, we have expectation for kids. And each expectation integrate the three dimension, like a discipline core idea, cross-cutting concept, and science and engineering practice. Discipline core idea is more like a force and motion. It's big idea instead of a small science concept. And a cross-cutting concept is like some big concept across different science discipline. For example, energy, right? In biology, chemistry, physics, we all talk about the energy, like a pattern, right? System, model, those kind of cross-cutting concept. And the framework really introduced an idea. It's like meaningful science learning can be achieved only if kids are involved in science and engineering practice. For example, drawing a modeling, right, and explain phenomena, or design a solution, or investigate some phenomena, or argue with peers. So that kind of practice. That's the new vision launched by the framework. And currently, there's a lot of states are using the NGSS, so next generation standard, and others are adapting the standards. So here's one example of the three-dimensional performance expectation. So we have a statement, develop a model that predicts and describes changes in particle motion, temperature, and the state of pure substance when thermal energy is added or removed. And this statement include three dimensions. For the science and engineering practice, we include developing and using a model. We can ask the kid to draw a model or write a description of their model or create a mathematical model, whatever. And there are two discipline core ideas, structure and properties of matter, and also energy. And also include a cross-cutting concept here. So cause and effect. So energy is a discipline core idea. At the same time, it is also a cross-cutting concept. So I just want to clarify this. In order to assess students' learning in terms like whether they meet the performance, three-dimensional performance expectation, is really challenging because we find it's very difficult to use multiple choice question to assess three-dimensional learning because there's scientific practice. And we also find some research indicated, construct responses or performance-based assessments are needed or be able to assess these three-dimensional learning. Well, some group like our group and also some group in like a Stanford, we create a lot of really good performance-based construct response assessment tasks for three-dimensional learning. Well, we also find a challenge for teacher to actually use the assessment in classroom because it's really time-consuming to score students' response. And we all know if teacher won't be able to receive the score timely, they won't be able to use the score to make instructor decision or adjust their teaching or prepare the lesson for case, then they are not going to use the assessment. I talked with some teachers in Georgia last year, and the teacher told me every weekend they brought the student homework back to home and spend half a day or even more to read the student responses. And they feel really excited when I introduced our approach to automatic score student responses. Here is one example from a project at Michigan. So Andy Edison was the lead of this carbon time project, where they developed, I think, a 57 construct response assessment and collect more than 1 million student responses. And in order to score the student responses, we assume if one person averagely can score 100 responses per hour, and we pay $20 for an hour, and to score this will cost 18,000 hours and $360,000. So it's a lot of money. But if we do have technology can help teacher to score automatically score the responses, and we're going to save time, save money, and the teacher will be able to use information to adjust the teaching or making a decision. That's the meaning and why we think it's really important to explore some technology. So the technology we use are machine learning, right? So why machine learning? I guess we all are familiar with automatic scoring even before we are familiar with machine learning, right? Think about the multiple choice question. When we use computer to automatically grade multiple choice question, what we did is we first tell the computer the rules. If students select A, the computer will assign a score 1. If otherwise, it's going to be 0, right? Computer is going to compare student response and assign a score, right? It's easy to do that because there's limited options we tell or rules we tell computer. But if we're doing construct responses or performance expectation, you just imagine students writing. It can be really diverse, and we are not able to raise a limited number of rules for computer. So what we try to do is we use machine learning. So we first hire some human experts to grade the student response according to some rubric, and then we supply the result from teacher or some human expert who graded the response, and then we supply the response to computer and let the computer to learn from human experts, and the computer will generate the rule by themselves. And once the rule is generated, some algorithmic model, then the computer can automatically score student responses. Currently, there are multiple different machine learning approach, like supervised machine learning, unsupervised, semi-supervised, reinforced machine learning. But generally, they're like a 3-step. The first step is we need to train the machine. And then before we test and use, we need to validate whether the algorithm is validate or not. So it means like the machine score is accurate or not. And then we test. So supervised machine learning as compared to unsupervised machine learning is the data usually will be labeled or scored by a human expert. But by using unsupervised machine learning, we are not going to label the data. Machine is going to identify the pattern from the raw data. For my work, like automatic scoring, we use supervised, unsupervised. We also use semi-supervised machine learning, which means we have part of the data are labeled, part of the data are unlabeled. If you look at currently, a lot of people using BERT, which we also use BERT, right? So the BERT is a pre-trained model. When they pre-train the model, it's unlabeled data. But when we fine-tune the model for our assessment task, we use labeled data, right? So kinds of trying to increase the accuracy and the efficiency of the training procedure. Reinforced machine learning is an approach to like have some rewarding when we receive when we receive the machine's score, we provide some feedback, then machine is going to learn from the feedback. It's similar. So the ChatGPT, so if you are familiar, ChatGPT actually was trained using reinforced machine learning approach. So they have a lot of experts to provide the feedback to the machine, so machine can gradually improve the performance. Currently, I primarily using natural language processing and computer vision for NLP. My colleague, like maybe 10 years ago, they use individual algorithm. When I started to work, I first used ensemble algorithm. We use 8 algorithms together to train and provide a prediction based upon their performance. We're going to assign weights to each algorithm. So the combination of the 8 algorithm, prediction will be the eventual outcome. And recently we are using BERT, which kind of save a lot of time for us. And in my group, and we also work with ETS, and we're trying to fine-tune BERT. We use some science education data to fine-tune a science education BERT, which we found performs better than BERT and a science BERT. So we have a conference paper proceeding submitted, which is under review. And we are also focusing on efficient NLP. We use prompt language learning zero-shot to try to reduce the effort of the human scoring part. So human, in order to train the algorithm, we need to hire human expert to human score. Is really, really time consuming and cost consuming in that part. So we're trying to reduce the effort. Some work is also undergoing, and we have a proceeding paper submitted to the AI conference. And for computer vision, we use some existing like a neural network to I have one study. We use the residual neural network, and we try to grade the students drawing model using computer. And we have another study, a chapter actually. We use the sequential convolutional neural network to grade the students' paper pencil drawing models. So these are some kind of work we are doing. The next section, I'm going to talk about how we apply AI to assess and promote next generation science learning. I want to pause here a little bit just in case if I have any questions.
No, I don't see anything in the chat. Anybody? So this is very interesting. So far we are very, everybody is riveted. What you mentioned is that scoring is expensive, but what I think we should pick up in the discussion, human scoring is also not perfect. So I think human and computers can maybe work together to improve scoring. So I think, again, there are so many aspects to that. And you mentioned the very important aspect that it's incredible effort to score with humans and that machines can help us. Also the case that unfortunately, unless you train on very detailed scoring guidelines, you always have human error there as well, obviously. Let's move on. Okay, if there's nothing in the chat, nobody wants to say anything.
I'll continue, and at the end of the talk, probably will leave time for question and answer. All right, so the next section, I have 3 driving questions intended to answer. I mentioned that I will be primarily using 3 studies, but actually there are more than 3 studies. I use the evidence to answer the 3 questions. The first one is how accurate of AI-based automatic scoring in assessing the next generation science learning. And a second question, what immediate information from the assessment can be available for instructional decision making? And as a third question is, how can we support teachers' AI-based assessment practice in classroom? So I'll start with the first one by introduce a framework that I use in my study. So in one piece, I write the practice and the theories. How can machine learning assist in innovative assessment practice in science education? I introduced and this framework, and the framework was also contributed by some other researchers. The framework basically highlight for assessment practice, no matter is formative or summative or small scale or large scale, I think it's very important to first identify the learning goals. So what are we going to assess? And the second aspect is we need to develop assessment to elicit student performance. And then based upon performance, we're going to interpret student, the observation we have in some form is maybe we ask a kids to write the response or draw a model. So that's something we're going to observe. But in order to interpret, sometimes we need a rubric. And we also need to, using the rubric to, grade the student responses, which is the part I think really challenging for complex assessment in classroom. And only teacher have a good understanding of student performance, they can make informed decision, instruct decision, and take the action for the instructional move in classroom. And eventually teacher will compare whether the instructional decision really makes sense to help kids to meet their learning goals or not. If not, maybe there are some further steps needed to take in order to facilitate that. So when we mentioned about using machine learning to automatically score student responses, the first question pump to people's mind usually is how accurate of AI-based automatic scoring, right? So that's the first question. In our work, we developed a framework for the machine learning-based next generation science assessment. So this is a evidence-based design. So we first identify the target performance expectations from the next generation science standards. And then we do some domain analysis, and we do some basically to analyze the 3 dimensions, and we do some domain modeling to identify some statement of how to meet what kind of evidence we needed in order to elicit the student performance and to infer their thinking and competence. And based upon that, we're going to develop the task and rubric. The next step in the dashboard is the machine learning part. So we collect the student response, and then we train human expert to score student response, and we use the response and the human score to train and develop algorithm model. And then we validate the algorithm model by compare machine score and a human score, right? To compare, to generate some accuracy measure like Cohen's kappa accuracy or whatever. There's a list of parameters we could look at, and once if most of the time we find maybe the accuracy measure were not so exciting or satisfied, then what we need to do, we need to go back and check to look at whether we need to tune the parameter of the model, or we need to look at the scoring procedure or the rubric or even the items. So it's a very lengthy and iterative process before we can have really valid and accurate algorithm model. Once we have the model, we can apply in classroom and support the teacher to make instructional decision. This is basically the procedure we're using. And I'll give an example here. So we're going to use the same performance expectation we introduced at the beginning. So when we do the domain analysis, basically we look at the statement and see, okay, students maybe have to develop a model that explains how particle motion changes when some more energy is transferred to or from substance without changing state. They need to be able to do a model, so involve the model in practice in order to meet this performance expectation. Then we do the domain modeling process. Basically, there are two components. The first one is to develop some evidence statement, like the model shows whatever, right? So, and then we have a fairness and equity framework to guide, to make sure that the assessment is inclusive and fair to students. So here's one assessment item we developed. So what we did, we first ask kids to observe a phenomena, right? A video. And in this video, researchers put a dye into water with different temperature. And the kids will observe what happened here. So then we ask the kids to draw a model to explain what they observe, the phenomena. And we ask also, in order to support, kids who have different, ability to draw a model, right? So we also ask them to write a description of their model. So here are two examples. The left side, we're going to see kids using some computer tools to draw. They use arrow to indicate the motion of the particles. They use red and black to indicate the particle, dye particle or water particle, right? So this is a drawing model, and this is the, to some degree, kids are able to identify dye particles, water particles, and identify the different temperature. There will be different, distribution of the particle, but they actually did not indicate the motion in terms like a different, like hot water. Usually the water motion, the speed will be higher than the cold water, right? That's the reason why the hot water crash with the dye particle is going to be stronger than the cold water. On the right side, we have a student write their explanation, basically explain their thinking and their explanation about the phenomena. So we developed a multi-aspect rubric. So we have 3 levels: beginning, developing, and proficient. And we have 2 aspects here. And for each level, we have some evidence. We require to see some evidence before we can assign students grade to this level. For this assessment item, we first present a phenomena, and we suppose kids are going to use their knowledge to construct a mental model in their mind. And then we ask kids to represent their mental model using multiple different approach. We're trying to provide a different avenue to provide an inclusive and equitable approach for every case, just in case they have different skills to write or to draw. And eventually, we understand not every case can draw a scientific model, but the purpose of learning is trying to help kids to improve and revise their model, and eventually they are able to develop scientific models, right? So, and for this study, we actually, for the project, we have more than 40,000 middle school students and more than 3,400 classrooms registered to use our assessment. And for this study, we randomly select 1,050 students just to, and a high human expert to grade the student response to train and deal with model. We select this number only, because, grade the student response is really very costly. So we're trying to save the cost. And we did is we train, we hire more than one expert to grade each student response, and we're going to check their inter-rater reliability. Once they meet the benchmark, and we're going to provide the consensus score to train the machine. And then once we have the algorithm model, we're going to use the model to predict a new assessment task. So, and then we're going to compare the machine score and a human score to generate some accuracy measures. It's not a reliability measure, it's accuracy measure, right? So once it meets some benchmark that we're going to be able to use with new student responses and the teachers. So here are some results. Because for this study, you actually automatically score joint model and written responses. So we have, I guess, 9 written and 6 joint model. So here are the accuracy measure. So actually the accuracy measure are, you're going to be able to say coherence kappa. This is the coherence kappa, not accuracy, sorry. And the measure actually are pretty good, very encouraging, because most you can see are about 0.7, right, for the joint model. And for written response, even better than joint models. For some maybe individual assessment item, occasionally we have a lower the accuracy, but most is, I think, is very encouraging. And I also presented some other results from our other research, basically including written argumentation, planning and carrying out investigations, and also write explanations. You're going to see the accuracy measure actually are pretty encouraging, except some individual item. So our conclusion from my prior research, I think the current status quo of AI-based NGSA scoring accuracy is comparable to human experts. Well, I think it's comparable because we found like even for human experts, for some item, it's really challenging for human to meet agreement. So my second question related to what immediate information from AI-based assessment can be available for informed decision-making. So we all understand if we're going to use the complex assessment and without automatic scoring, teacher will not be able to have students score immediately. But if teacher have the score immediately, what kind of information they are going to be able to mine from the score? That's a problem, because I was a teacher. I always feel challenging if I were provide some statistical information about student performance without some unpacking or interpretation. So how to help teacher to interpret that the raw score, which is a work that I worked with my colleague Kevin Hoddick and Wen Chao. We published a research assessing argumentation using machine learning and cognitive diagnostic modeling to mine the automatic scores. So basically, for this research, we're focusing on argumentation. We use Turing's argumentation framework. Basically, Jonathan Osborne from Stanford University cited this Turing's framework to develop a learning progression in 2016. And our project based upon that learning progression in 2016. So Turing's framework basically tell us there are 2 types of argument. The first type is, well, you make an argument, right? So you make a claim, you have evidence to you have evidence, and you are able to link your evidence with your claim. So we call that like a warrant or a reasoning, right? And a different type is you could criticize some of these arguments, right? Try to refute their argument. And then in that sense, people will also need to make a claim, need to have evidence and a warrant. And sometimes, they need to, this is kind of rebuttal, some of the refute some of these else claim. It's more challenging, right? It's even more challenging. So in our work, we developed 19 argumentation assessment item within 3 clusters. So for each cluster, we have, I think, 6 to 8 assessment item. Well, what we did for that is because we find that if we kind of split the big arguments into some smaller components, it's going to be easier for computer to derive automatic score. If the question is very complex, then students' responses will be very diverse. It's going to be more challenging to derive automatic scores. In this sense, for example, we have an assessment, we present a phenomena to students, and we ask kids to make a scientific argument about this. And each question will link to the learning progression developed by Jonas Osborne's group, like constructing or critiquing, that kind of, for this one is construct a complete argument. So here's our rubric. We basically look at the 3 components, like whether students have a claim, they have evidence, or they have a warrant for their argument. So I think claim is very easy to understand. For example, the sugar was dissolved is a claim, right? And evidence is, for example, in this phenomena, kids can say, well, it's no longer visible. That's some evidence. Why the no longer visible can support the sugar was dissolved? Because particles break up until the spread out throughout the liquid, right? So that kind of components we look at. In the learning progression, the authors basically have an assumption that if we, for each argument, if the scenario or the argument is more complex, sometimes you need to identify maybe more claim or more evidence, or use multiple pieces of warrant to support, to link the evidence to claim. And as you have more numbers of the elements, it's going to increase the cognitive load for people. Like when I argue with you, if I need to make more claim, I need to use more evidence, it's going to be more challenging for me because it basically need higher cognitive load for me to manage all the activity. So that's the basic assumption. And we use the same procedure as we just mentioned for developing the automatic scoring. And the next step, once we have the score for the 19 items, we all have good score, automatic score. And then we developed a cognitive diagnostic modeling, a Q matrix. And this Q matrix basically based upon the number of claim, warrant, and evidence. And we code each assessment item based upon the learning progression. And we use this Q matrix to infer the students' mastery patterns. And we found like 70%, basically students were clustered into 21 groups, and 70% of students are distributed in 9 most frequent groups, right? So basically tell us, like, for the first group in the table, this group of students, 30.7% of students in this group are able to make 3 claims, and one warrant, one evidence. So that's the highest level they are able to do, right? I think this approach basically mine the raw data and tell teachers about their students' cognitive pattern in terms like argumentation, and it also tell teacher like some information beyond their score. So we use CDM. Basically we can generate student like ability measure, right? So, but if even students have the same ability measure, if we look at their cognitive pattern, they can still be different, right? Here's one example, including 3 students achieve the same ability measure. But if we look at their performance on the claim, evidence, and the warrant, we're going to find they're significantly different. And the first students basically can make one, relatively good claim and use 2 pieces of evidence, but they're not able to actually link the evidence to support the claim, right? But the second students like can it's very challenging for this student to make a good claim, but the students identified some evidence and council are able to identify some warrant, but it's not quite as strong, and the evidence were not able to support the claim. And the last case is what the student make a good claim and the evidence was really low, so not able to identify good evidence to support the claim. We expect teacher, we can do more work because this is some, I think it's some work we start to work, but we think in order for teacher to use this assessment task, the information here, we need to provide some support to teacher, right? So not every teacher can transform score or this kind of information into practice immediately. That's the reason I'm going to present the 3rd study. So what kind of support we develop to support teacher? Basically, for the second question, our answer is the complex cognitive level information that was not available immediately before automatic scoring are available could be provided to teachers for informed decision now with the help of artificial intelligence. But in order to support a teacher, which is some work that we are doing currently on my NSF project, so we try to support a teacher to use AI-based score to do good assessment practice in classroom. So what we did is we assume that teachers' instruction decision is always centered in their instruction. But in order to really support a teacher to make make good instruction decision and facilitate the students' 3-dimensional learning, we need to align the learning goals and the instruction decision making with the learning outcome, right? So the 3 need to be aligned. Well, the most challenging part is the instruction decision. How can we make sure that instruction decision aligned with 3-dimensional learning goals? We assume that first the teacher need to have 3-dimensional knowledge and belief, right? And we also assume that we need to have 3-dimensional assessment. And however, even we have 3-dimensional assessment and we have a technique to mine the raw score, to automatic score and then mine the raw score, we think it's very important that we present some essential information to teacher and in a way that teacher can understand, especially if it's in classroom, right? So teacher don't have a lot of time to look at the score. So we call this all-to-R, represent automatically generated assessment report. So one work we are developing all-to-Rs. So we use human-centered design to do this. So we hope that we can provide a good all-to-R for teacher to use in classroom. A second part of the work is focusing on if teacher understands 3D knowledge and they have the belief, are they able to transform the O2R information into practice? Most of the case, I believe the answer is no, because not every teacher have the essential, the pedagogical content knowledge to transform that. So our work focusing on developing the pedagogical content knowledge support or instruction strategy to support the teacher to make their instruction decision or use the O2R. This is part of our work. And this project is currently ongoing. So I'm going to present some preliminary result. I'm not going to be able to present some final result. So in terms like the designing O2Rs, we are using a human-centered design approach. Basically, we identify we identified some cognitive demand for teacher. So some factors will impact teachers' cognitive demand when they interpret the score, which is like the depth of the data mining, the content, and the synthesis levels of information. And in order to address this, we need to use our design to reduce the cognitive loads for teacher. Then we focus on what kind of function we're going to build up into the auto score, O2R, and how are we going to present the information. Right on the right is one version of our O2R design. Like we have some diagnostic information provided to teacher. We have the pedagogical, the teaching strategy provided to teacher. We also have the students' performance and the historical data. We're still working on this and revising, and I guess this is not the most current version of, because we are still revising the O2R. And we developed a platform, and we called AI Scholar. The platform basically link the researcher, students, and the teacher together. Researcher can develop a model, and then we put them into the server, and students can submit their response, looking at the assessment, and teacher can manage the students and look at the student performance and making some decision. This platform is now we already developed, and we are piloting this platform with teacher. That we are revising the platform, and we also have already developed some instruction strategy for teachers PCK, and there are 4 types of instruction strategy, which are also currently undergoing work. So I'm not going to go deep here. So the primary conclusion from here is really preliminary conclusion. So the presentation of AI-based assessment results in O2Rs matters according to our cognitive lab interview from teacher, as it impacts how teachers attend to and interpret the scores. And but we also realized much is needed to study how to support teachers in making use of O2Rs for instructional decision. This is basically the 3 study. I hope that briefly illustrate how we apply AI to assess and promote next generation science learning. And last, I wanted to thanks my collaborators and also acknowledge the grant support our work. Thank you so much. I'd like to take questions.
Please.
I have a question. I'm not Laura Dwyer, I'm Henry Brown, but so what I'd like to understand is how far are you in terms of providing that scaffolding to teachers? Because it seems to me that's it's the critical part that isn't so easily dealt with by technology, because you have so much heterogeneity in terms of where teachers are, as you know, their content knowledge, their belief systems, their openness to these new approaches. So how many teachers have you been working with, and what are you finding in that score? Thank you. Very, very exciting work.
Thank you so much for your question. where you ask are some work we are currently doing. And this is our second year. And our goal is going to work with up to 36 or even more, because we're going to be working with teachers from Georgia, California, Chicago, and Michigan. We're going to have, I guess, more than 40 teachers every year to work and use the instructor strategy support. Hopefully from next year. And currently, we are working with a small group of teachers to develop the pedagogical content knowledge support for teachers. So I think we have experts in science education who are familiar with teacher instruction. And we have a framework to develop the instructional support. But I have no data right now to say like whether it's the efficiency and the efficacy of the support right now. I think currently our major work are focusing on developing the auto-R, so auto report.
Okay, thank you. Thank you.
You're welcome.
I have a question.
Sure.
Very nice meeting you, Xiaoming, through the Zoom session. So throughout the process, you introduced the AI, how AI is used in automated scoring, and how this can provide feedback for teachers and students. Compare with the difficulty level of the content area and the domain area. You mentioned the some experiment examples. Do you think the whole algorithm can be applied to all different kinds of subjects because you are using the natural language processing convolutionary neural network methods to do it? Just from your observation, I want to know the difficulty level. Are they appropriate throughout the K-12 or only through the K-2 from what you have studied so far for elementary, middle school level? Yeah.
Yes, that's a really good question. So far, I think we have the technology to score constructed responses and join models. That's the first point. We have the technology. The second point is we are still improving the technology, the AI and algorithm, right? That's the reason why we are trying to develop like a science ad BERT, and we are trying to develop some prompt like efficient NLP to score. There are also some challenging there means. And the third part is you ask whether the applicability, I guess, right, to different level and a different subject. I think potentially the technology can be applied in different discipline and different good level. However, like our current work, we find not every assessment item is easily to develop automatic scoring algorithm, right? Some assessment item is more easier than the others in terms like developing the algorithm models. So that being said, there's still some work need to get down to analyze and to examine the assessment item feature, how that feature related to the feasibility of automatic scoring, right? So I have a meta-analysis research, I think is here, this one. So myself, Shi, and Russ Nim in 2020, we used a meta-analysis approach to analyze 110 assessment item. So in terms like the machine-human agreement, we are trying to look at what's the moderators for the machine-human agreement, and we identified some factors kinds of related to the scoring accuracy. But I think that's based upon some prior developed assessment task. And definitely, I think a lot of efforts needed to be dedicated to examine the assessment item feature and how can we easily develop assessment items so that we can easily develop the algorithm.
Did you notice that when you use cognitive diagnostic models combined with this, when I did some research related to cognitive diagnostic models, when you applied multidimensional and multi-level attributes and the fine-tuned attributes need to be developed first and very clearly when you first design items.
Yes.
This also applied to AI algorithm scoring as well, right?
Yes. Yes.
Okay. Thank you. Very nice presentation. Yeah.
Thank
Very
you
nice.
so much.
Thank you so much. So, are there other questions? We're a little bit over time. If there are other pressing questions, but I think we have the contact of your website is up. So if somebody has a pressing questions, maybe you can start reading all those papers.
Yes, I have please feel free to reach out to me if you have any questions or you're interested in my work. And I'm very glad to have collaborations or like to discuss about your interest and whatever you want to talk with me. Feel free to send me email.
Yeah, great. So I will certainly pick that up, and I think we should all thank our speaker today. This is a really exciting time because things are really changing extremely fast. And as you just mentioned, there are other areas, I think in medical licensing I know of, and of course essay scoring. Just yesterday there was the big reveal of GPT-4, so there are new things coming. So GPT can now interpret images and can actually tell you whether an image is funny or correct or incorrect, and even convert it into code. I want to end this session really with thanking everybody who showed up, thanking our speaker in particular, and also tell you that there will be one more talk in this series in this semester. So Jenny Young will talk about actually international level automated scoring, and that will also be very, very interesting. So hope everybody can show up, and thank you again, Xiaoming. It was very, very nice.
Thank you so much for inviting me.